Okay, so this is the outside of class examples for 2.7. And so there's only actually one. So we're going to do it. Paper view, let's try it. Okay. I've decided that I prefer to make videos than mop the floor. I mop the floor in between some videos here. Uh, but I think I would prefer to just lay on the couch uh, than both of those activities, than either of those activities, I guess. Okay, so let's see here. So this is problem 24. Some of the highest tides in the world occur in the Bay of Fundy on the Atlantic coast of Canada. At Hopewell Cape, the water depth at low tide is 2.0 meters and the high tide is about 12.0 meters. The natural period of oscillation is a little more than 12 hours, and on June 30th, 2009, the high tide occurred at 6:45 a.m. This helps us explain the following model for the water depth in meters as a function of time in hours after midnight on that day. D equals this. The T, I think, is standing for time after midnight on that day. How fast was the tide rising or falling at the following times? And in the book, they had A, B, C, D, E, F, and I just did one of them. So A. So if you're wondering following times, and there's only one of them there, well, that's because. So if you wanted to go try the others, you certainly could. And so now it's asking how fast was the tide rising? What's D in meters, right? D is in meters. So if I just put in um, time right here, remember our time was in hours after midnight. And so our time is, because after midnight, 3 a.m., that's 3 hours. So we can just put in 3. So if I just went in and put in 3 in this formula, that should not give me how fast the tide is rising, but that should just give me the depth of the water at that time, is what it should give in meters. And so I want to know how fast was the tide rising or falling, if it's falling, at that time. So what I need when it asks me how fast something is happening, that's like its velocity. I need to find its derivative. And so that's what I'm going to do. So I have to take the derivative of this. And so I'm going to put d at t equals 7 plus 5 and then cosine of, and then for the input in there, now this is style, so you could do whatever you wanted. I would prefer to multiply that together. And so, but you do you. So this would be 0.50t, 3t minus, and then 0.5 times, oh, that could get nasty. I might be not happy that I multiplied that together, but I'm going to go ahead and go for it. 0.503 times 6.75 equals, okay, it's not as bad as I thought it was going to maybe be. Okay, so if I take the derivative of 7, that's a constant, and I'm done with it. Okay, so d prime at t, okay. And if you're looking at the units here, I mean, another way of saying this, I know it's going to look funny, but dd, d capital D, dt. And so this is going to be meters per hours, right? Meters per hour, right? And so I'm just going to write it like both of those, just I'll have the units on it. So the derivative of 7 is 0 plus, and then 5 times a function, the 5 just holds still, right? And then now I'm realizing that this function is just not t. So if that was just cosine of t, then when I took the derivative of that, I wouldn't have to use the chain rule because I know the derivative of the cosine of t, right? If I'm finding d dt of the cosine of t, that would equal to negative sine of t, right? But I don't have just simply t. I have this inside there. And so remember how you do the chain rule is you take the derivative of the inside, uh, the derivative of the outside, evaluated at the same inside, multiplied by the derivative of the inside. And so what I usually like to do is I like to note to myself, I'm going to put 5 and I'm going to put parentheses like that, just so that the 5's on the outside. And then this right here, I'm going to put my finger over the 5. This cosine, right? Cosine of whatever here is my outside function. So I say I want to take the derivative of the outside. So I'm going to take the derivative of cosine. So that's negative sine. Negative sine. Notice I've already got those parentheses. Evaluated at the same inside, right? Multiplied. Well, I'm going to write the inside down here. The inside is 0.0503t minus 3.39525. Almost didn't fit on that paper. You're like, it did not fit on that paper. So the 5 is on the outside, right? And I put parentheses, and I'm saying the derivative of cosine is negative sine. This is not subtract, it's multiply. 5 times this. So that's why I put the parentheses so that I wouldn't mess that up. And so evaluated at the same inside. So the same inside is 0.503t. I'm going to have more room. Minus 3.39525 multiplied by the derivative of the inside. And the derivative of the inside, well, the derivative of 0.503t is 0.503. I'm going to put parentheses, multiplied by. And then the derivative of a constant is 0. And then I'll be able to put my bracket. So I just have to put that together. So it's a little bit messy. So, but I've kind of handled it, I think, by using some parentheses. So the derivative of 7 was 0. The 5 was a constant, so it held still. And then I had to take the derivative of something complicated, so I put parentheses, so I just wouldn't mess it up. And now this is all multiply. 5 times negative of sine of this stuff times 0.503. So I think on my calculator, I'm going to put in the calculator 5 times negative 0.503, which becomes negative 2.515 sine of 0.503t minus 3.39525. Lol. And so there is my derivative. So it's asking me how fast is the tide rising at this certain time. This is the speed that the tide is rising at all applicable times. And I'm going to put in t is 3. So 3. I'm going to put a 3 there. Get a 3 there. Ooh, this is going to be a challenge to know how to get this calculator in radians for me. You would think, since I went and mopped the floor, that I would have said to myself, you don't have a calculator that you're comfortable with. It's already in radians. And so why don't you grab a calculator that you're comfortable with? But whatever. It is better to use a calculator that you're comfortable with when you're taking a test or making a video. And 0.503 times 3 minus 3.39525 in the parenthesis. That should give us, so I'm getting 2.39. I don't know that I need to take any more places than that. And this is, remember, I put it like this so I would know the units, meters per hour. And so at 3 a.m., the tide is actually rising 2.4 meters per hour right at that exact moment. That's what the tide is doing. And I was going to make sure I didn't make a mistake there because that was some decimals there. What example was this? 2.7 and number 24 out of your book. So what am I on now? I'm looking at, I'm going on Canvas because that's where I've put the solution guide for you and for me. 2.6 I'm at. .7 now, and this is problem 24. Yeah, they got exactly the same that as we did. They did also note, which I said but didn't write, but they did also note, comma, it's rising. Okay, so we did a lovely job on that. So we want to stop recording and